So we have been looking at the solution for the Burke-Schumann problem, and what we can now figure out is we are interested in the flame height. Surprisingly, for tall laminar flames, that means we still have the situation of Peckley number being quite large but still not into the turbulent regime. The Burke-Schumann solution gives a very good prediction of the flame height, and this was significant back in 1928 if you think about it. So the way you actually can find out the flame height is, as I said, gamma equal to 0 is going to give you the flame shape, and of course it's going to switch from a underventilated flame on the one side to a overventilated flame on the other side. So depending upon whether it is underventilated or overventilated, you need to evaluate this expression setting gamma equal to 0 for the eta, alright. Now plugging in psi equal to either 0 or 1, right. So with this you can get the flame shape. So let's do this for at least one of those. So for the overventilated case, say psi equal to 0, eta max, that is the height of the flame. So you can now plug this in here. Of course what happens is you now have a gamma equal to 0, and then you have this expression which is the series summation, and we are trying to find out eta on top of this exponent sitting there with a negative sign in each and every term, right. That is quite difficult to do. So one thing you can do is to recognize how the series is going to behave, and then say as a first approximation, let's not worry about the series, let's consider only the first term in the series, right, as a leading term, and then the remaining terms are corrections to it. Therefore approximate to the first term in the summation with phi 1 equals 3.83. This is something that you can find out from the Bessel's function tables. So there is like a table of special functions which will give you values of these zeros. So we are looking at the Bessel function of first kind, the first 0 of that, you will find that in the table phi 1 is equal to 3.83. Keep this in mind, and then you get a eta max. All you have to do is get rid of the summation. Wherever you have n, you just put equal to 1 because you're looking at only the first term, and this thing goes to the left hand side, this thing comes down, and then you have this, and then you find that this is actually e to the negative, right. So if you now want to flip everything and take a natural logarithm, then you will get a phi n squared eta, eta equals eta max, and therefore if you now get the phi n squared also to the denominator on the other side, you will get it as 1 over phi 1 squared natural logarithm 2 twice of 1 plus nu times c j1 of c phi 1 divided by nu minus 1 plus nu c squared. When this goes to the left hand side, you get a negative sign, so this flips times phi 1 j naught of phi 1, right. So this gives you a good idea of what the flame length should be. But what do we learn from this? okay. Do we know how the flame is going to how the flame length is going, as a matter of fact it's difficult to find out how the flame shape is going to be with this expression, and as I said this is how the flame looks like. But if you now look at this expression for the flame length, you can't see the dependencies in the problem, right. So how do you set up this problem? You now have these coaxial pipes, and then you want to send fuel and oxidizer together at particular, shouldn't say together, I mean in each of these pipes at the same velocity. That's what I meant by together, right. So the same velocity, and the C is your variable, as I said, and your YF0 and YO0 are your control variables. These are the ones that you're trying to control. Depending upon YF0 and YO0, the nu is going to get fixed, right. So you can do all that, but how does it vary? Or for that matter, is the flow velocity showing up here? No, because the flow, this parameter, this equation was primarily, this solution was primarily obtained for neglecting the axial diffusion. All right. So we will do a couple of things now. First, let's think about what happens when you now try to keep axial diffusion. All right, and I'm not going to solve that problem. I'll let you figure that, but I'll tell you what are the possible steps that can get in there, and the second thing is, and then what are the consequences, and the second thing is, let's look at the dependencies. Okay, so the first thing is, if you consider axial diffusion. Diffusion is included rather than neglected, right. We would have U over D dou beta by dou z equal to dou squared beta by dou z squared plus 1 over r dou by dou r or dou beta by dou r. Previously we did not have this term. We are now trying to keep this, right. So what's the consequence of this? First of all, you could say that R is still governed to second order, and therefore it requires two boundary conditions. The two boundaries in R are R equals 0 and R equals B, and I would like to supply boundary conditions there, and I expect to have symmetry boundary condition at R equal to 0, so dou beta by dou R is equal to 0. That's a Neumann condition, and at the wall I have a rigid non-porous wall, so I can't have diffusion through that wall, so I still have no diffusion mass flux, which amounts to dou beta by dou R is equal to 0 at R equals B at the outer wall, and so I get Neumann boundary condition there. As far as the Z boundaries are concerned, this is now suddenly beginning to be governed by second order. Previously it was governed only to first order. Now you have actually a second order term that's governing this, right. So whatever we neglected was somewhat pretty important. I mean it actually reduces the order of the equation by 1, which means it doesn't permit an additional boundary condition, whereas this one demands an additional boundary condition. That means you have to give two boundary conditions in Z. Okay, the domain for Z is Z equal to 0, which is something that we considered earlier, and Z equals infinity. So you now can actually go all the way up to infinity here, and that's where you have to supply the boundary condition. What do I know about beta at Z equal to infinity or its derivative? And now you have a very important situation. You see, because you have this governed to second order, not only it demands two boundary conditions, but it can also permit a boundary condition in the derivative. Okay, so we already had two boundary conditions in derivatives here, and if you now allow, if this admits boundary conditions in derivative, that means you can specify dou beta by dou z at R equal to z equal to 0, and or dou beta by dou z at z equals infinity, then you don't have a unique solution, because you are supplying Neumann boundary conditions everywhere. Therefore you need to supply Dirichlet boundary condition somewhere. Okay. Now previously we could supply only Dirichlet boundary condition because this is governed to first order and you could give only Dirichlet data. Now it is governed to second order, that means you can have a not only Dirichlet but also a mixture of Dirichlet and Neumann. What is that? How could I get that? So now you have a choice of different boundary conditions that you can give, okay, and they should mean something physically, or in other words we should now interpret that physically, okay. So if you go back to your original problem, right, so beta is now governed to second order in Z, so need 2 BCs in Z for beta, which implies Z equal to 0 and Z equal to infinity, okay. Also can admit Neumann BCs in beta, that is could specify dou beta by dou Z at Z equal to 0 or infinity, but can't specify all Neumann BCs, that is keeping dou beta by dou R equal to 0 at R equal to 0 and B as others, okay, because this would lead to a non-unique solution. Therefore could retain Dirichlet BC or mixed, which is Dirichlet plus Neumann BC. All right. All we can say, in fact, at Z equals infinity you don't have too much of a room to play with on what should be the boundary condition. All we can say and hope for at Z equal to infinity is that beta should be bounded. We can't specify values, we can't specify derivatives, simply because you are expecting to get a exponential solution, and since you have a second derivative now, you can actually admit a e to the plus some constant times, let's say phi n squared, e to the plus phi n squared eta plus some constant times e to the minus phi n squared eta. And if you now admit the coefficient to e to the plus phi n squared eta, as eta tends to infinity, that solution is going to blow up. So by specifying that Z equals infinity, beta should be bounded, we can get rid of the exponentially growing part of the solution and retain only the exponentially decaying part of the solution as before. Alright. So at Z equals infinity we merely specify that beta remains bounded, which eliminates the exponentially growing solution in beta. in eta, I'm sorry, right, and retains only the exponentially decaying solution in eta as before. As a matter of fact, that's what boundary conditions are supposed to do. Boundary conditions are supposed to evaluate constants of integration that are appearing as coefficients to solutions, and by just merely saying that beta should remain bounded as a boundary condition at z equal to 0, we evaluate the coefficient of the exponentially growing solution in eta as 0. So we have done the job as far as that particular boundary condition is concerned. Then comes this, right. Here is where it's important for us to decide whether we want to have a Dirichlet boundary condition or a mixed boundary condition. So this question of whether we want to have a Dirichlet boundary condition or mixed boundary condition arises primarily at z equal to 0, at the lip of the burner, right. That means it's now possible when you admit or include axial diffusion that you have a choice of boundary conditions. Either it could be the Dirichlet boundary condition that we used before, which we didn't have a choice about earlier, or we can use the mixed boundary condition now. The question is, what does the mixed boundary condition really mean, right. So let's now think about the flow that is coming through one of these ports, and now we are admitting axial diffusion, right. So if you now go back and look at the solution, so or if you now try to map the solution and say you have a flame that is supposed to be here, right. What does that mean? This really means that you have a fuel rich region over here. This is the stoichiometric surface, this is the fuel lean region around, okay, and there is a progressive change in the mixture fraction from a pure fuel or more fuel in the middle progressively to stoichiometric and then fuel lean, okay. It's a varying region over there. What that means is, if you now look at it along the axial direction or the streamwise direction, you have more fuel here than here, right. So it is sort of like as the fuel is coming out and flows up into the domain, and you don't have the tube anymore, it's now got into the domain, it looks around and then sees, wait a minute, I am not there, so let me go there, right. And then once it goes there, it says, hey, wait a minute, I am not there, let me go there. What is that? That's axial diffusion, okay. Now of course you might think, wait a minute, don't we have all the flow kind of coming up? Yeah, that's what we had in premix flames also, right. So but at that time what happened? We now decided that you're going to have a flame and the reactants are coming in, and then they all getting converted to products, and when the products are formed they suddenly get formed and then look around and then find it's all products over here, no products over here, can I diffuse backwards, right, and it tries to diffuse against the current meaning the convection, right, and it succeeds to some extent, just as well as the heat gets conducted upstream even as the convection is actually carrying the enthalpy this way. If the heat could penetrate, why can't mass, right, it's after all both of them are transport processes. Similarly here you could have a current that's set up upwards, but you could have a reverse diffusion, that's for the fuel. But think about the oxidizer doesn't even have to fight the current, right. The oxidizer is here and it finds, wait a minute, there is more fuel over there, right, can I now go up, right. So along with actually convecting, it begins to diffuse up, right. So these axial diffusion processes, the question is how good are they, is a question of how well are they competing with convection. So when you don't have a large convective effect, that means you're at fairly low velocities, right, in simple English, then you can now expect the axial diffusion to be more predominant, alright. So this is a problem where the convection could predominate axial diffusion but balances radial diffusion. Alright. So the balance between radial diffusion and convection is the centerpiece of this, but alongside at low convective effects you could have a significant contribution from axial diffusion as well. If you now think about that, so you now say fuel is coming out like this, diffusing like this, and then going backwards. Oxidizer comes like this, diffuses like this, or rather it can even diffuse like this and then goes backwards. If it did, then the question is, how good is the Dirichlet data? Correct. We were imposing, saying at the lip of the burner you have only fuel here and only oxidizer here. That's what we did, right? But that need not be the case. You could have the incoming fuel get contaminated by oxidizer that is diffusing from the other side, right? Or products as a matter of fact, and similarly the oxidizer. So where can I expect to be sure that I don't have any contamination? Far upstream. Because you have a convection, there is a certain length scale associated with the diffusion in competition with the convection, right? And beyond that length scale you can hope to have pure fuel and pure oxidizer. But how do I know what that is unless I solve? And for me to solve I need to know the boundary conditions. So where do I go in search of the boundary? Do I want to now take like a minus infinity to plus infinity in Z for the domain? When in fact I am interested in what's happening here, that's where what is called as a flux BC comes into picture, right? So we could now think about a flux boundary condition which is essentially a species balance that's integrated over a control volume for each of the species from minus infinity for the Z to over here, knowing that this is going to be all fuel. Alright. So if you now take the governing equations and integrate within this control volume, what you can now expect is we now know that you can say rho u yf minus rho d dou y, right, at Z equal to 0 should be rho u yf minus rho d yf by dou z at Z equals minus infinity. There is hardly anything that's going on along the walls. You neither have convection nor diffusion along these walls, right? So the control volume here that we are looking at is having exchange only at this surface and this surface at infinity, far upstream. Far upstream we know that you don't have, you have pure fuel, and therefore you don't have any fuel concentration gradients, so you don't have any diffusion to talk about, right? So this goes away and you can directly now say this is equal to so you can say rho u yf at Z equal to 0 minus rho d dou yf by dou z at Z equal to 0 equals rho u yf naught, right? And then you can say yf at Z equal to 0 minus d over u dou yf by dou z equal to 0 equals yf naught. So what has happened now? Previously we ignored this term. We did not consider any diffusion that was happening axially across the inlet to your domain. We simply said yf at Z equal to 0 is yf naught, but now you have to subtract that amount that is actually diffused, you see. And what is that going to be like? In fact, if you think about axial diffusion, including axial diffusion, then the problem becomes somewhat symmetric in both z and eta. That means you don't have to worry about z and r. That means if you now thought that the length scale of your r dimension was b, the Bernoulli width, what you're essentially saying is it's diffusing along the radial direction just as well as it's diffusing along the axial direction, at least to begin with, but that's a consideration. We will have to evaluate how much this is versus that, okay, and that will be done by the Peclet number. So if you were to now say that z is also going to be of the order of b, and then say so for non-dimensionalization of z as eta equals z by b, okay, same length scale for axial as well as diffusion. This was not the case before. We didn't have an axial diffusion length scale unless we actually started looking at what is the flow versus the diffusion length scale. So we had to do something like z by b divided by u by b squared by d, and then we came up with a new non-dimensional number, coordinate eta last time. But if you do this, then yf at z equal to 0 minus, you now get a b out here, right? So you can have a d yf naught or yf minus 1 over Peclet dou yf by dou psi at z equal to 0 equals yf naught, right? Now this is what is called as a flux boundary condition, and it's a mixed boundary condition. It now has a linear combination of value and derivative together, right? This is sort of like a yf plus b dou yf by dou psi, where a is equal to 1, b is equal to minus 1 over Peclet. Okay, it's a linear combination. That's what is a mixed boundary condition. So the summary of what we are talking about is that consideration of axial diffusion permits diffusion at the inlet boundary, right, and leads to a mixed boundary condition. Now mixed boundary condition is all right because it still involves some Dirichlet data, right? Yes. I'm sorry, did I keep making that mistake? Sorry, Anita are Greek. Sorry. Right, as a matter of fact, psi is the equivalent of x and eta is actually equivalent of what? It's not z, it is actually h. So that's why the confusion. We should have been using zeta. All right. So now question. We can ask two questions. One, all right, I have axial diffusion, okay, but let me insist on having only the Dirichlet boundary condition as before. That's possible. Mathematically that's correct, okay. It may not be physically correct in some situation, but mathematically that's okay, you can do that. What would be the effect of considering axial diffusion, okay, with just a Dirichlet boundary condition as before? The answer is, that now begins to depend on a new parameter which is called Peclet number. Before we didn't have Peclet number, we had a non-dimensional governing equation without any parameters. But now what will happen is you will have a 1 over Peclet squared showing up, and clearly what that means is, as Peclet number is large, the axial diffusion effect relative to axial convection is going to be small. Okay, that means axial diffusion is important mainly for small Peclet numbers, right? So Peclet number here is obviously UB divided by D. This is the mass diffusion counterpart of Reynolds number that I pointed out yesterday, and what that means is at small Peclet numbers your convection is not as convection is not predominating over diffusion. Okay, diffusion is quite important, and therefore you will now end up with a flame that's a bit fatter and shorter, right? So this is this is the way you're going to get things to go as Peclet number increases. And the Burke-Schumann solution that we saw so far, neglecting axial diffusion, is in the limit of infinite Peclet number. Alright, so the job of axial diffusion is to make the flame shorter, because you have more mixing happening axially as well as radially, and therefore you get a shorter and a bit fatter flame correspondingly. Then the next question that we have to ask is, well, fine, now I have axial diffusion, and then I look at the problem and then decide that I want to have a mixed boundary condition, which means I want to have a flux boundary condition like this. What do? How does the flame look like, right? The answer is, if you now had a Burke-Schumann solution with axial diffusion and Dirichlet boundary conditions, if you had a flame that looked like that, your flux BCs are going to actually make sure that of course your domain starts here, right? Your flame starts somewhere there. That means the flame is no longer going to be attached to the rim of the burner. Right? Why was it attached to the rim of the burner before? Because we did not permit axial diffusion across the interface, across the inlet, and therefore when the fuel and oxidizer met, the first opportunity at which they could meet was right at the burner lip, and they meet at stoichiometric proportions there and then on in a certain curved manner, and therefore the stoichiometric surface starts from the lip of the burner, like what we have shown here. But when you have axial diffusion taken into account, you can now permit mixing to happen this way across upstream of the inlet to the domain, and therefore you could find the fuel and oxidizer being in stoichiometric proportions away from the lip of the burner. That's possible, and we are not strictly speaking drawing what's happening inside, because we are not solving for it. Our boundary condition is still applied only here, and our solution starts only into this domain, right? So we don't know exactly what's happening, but this is permitted. Okay, so this is the consequence of having flux boundary conditions along with axial diffusion taken into account in the case of the Burke-Schumann problem. In general, if you look at the literature, the term Burke-Schumann flame stands for infinite chemistry, right? That means we have not really bothered about solving anything to do with finite rate chemical kinetics. So you can have, for example, Burke-Schumann spray flame, like you have a spray of droplets, and the droplets are burning, and what it means is basically that as the droplets evaporate and the vapor from the droplet is mixing into the oxidizer, let's say you're looking at fuel fuel droplets, fuel spray, right. Wherever you find the fuel vapor in stoichiometric proportion with the oxidizer, ambient gaseous oxidizer mixing into this, you now form a flame. That's a Burke-Schumann flame, okay, and that's what you would call as a Burke-Schumann spray flame, right. You can also have something called a Burke-Schumann jet diffusion flame, or a jet Burke-Schumann flame. So what that would mean is I don't have to have walls. Burke and Schumann were very clever, you see, they made these walls so that they don't worry about entrainment from the surroundings, right. This is a purely species mixing and convection problem. They isolated the most important aspects of this very, very well, okay. So you could now think about a jet flame in which you have only the fuel coming out, you have quiescent oxidizer everywhere, right, and it now gets entrained as well as diffuse, and in this flow field you could now think about wherever the fuel and oxidizer are present in stoichiometric proportions, and that would be your Burke-Schumann jet flame. So on the one hand the Burke-Schumann problem would actually mean this problem. A Burke-Schumann flame in the literature now comes to mean any stoichiometric surface that is now coincident with a Burke-Schumann flame. That's essentially what it means. That means we are adopting the infinite rate chemistry assumption, or the flame sheet assumption, or the mixed is burnt approach, or whatever it is. You can call it in any other way. Anyway, this is what we are talking about. The second thing that we decided to talk about when we looked at this expression was, what about the dependence on the flame height, right. Do we get these dependencies? We don't get to see that right there, okay, and part of the reason was Peclet number didn't show up because we had supposed infinite Peclet number there. In this kind of a formulation you could hope to actually begin to see Peclet number show up in places, and that would actually now denote the flow velocity relative to diffusion, right, and then you can begin to see what's the effect of flow velocity, but still the expressions are going to be so complicated you don't get the physical feel, right. So it's easy for us to actually look at what happens in a order of magnitude manner. So order of magnitude, all we are saying in this problem is a axial convection balances radial diffusion, right. So what that means is you can now look at the axial diffusion, axial convection time scale. An axial convection time scale is essentially, let us suppose that you now have the flame length as LF. So axial convection time is essentially the residence time of reactants in the flame. The residence time is actually a very, very basic and important idea that you will find thought about in design of combustors and so on. So whenever you want to actually design the length of a furnace, right, particularly for diffusion flames, previously we saw what happens when you have ramjets and so on, or afterburners. The flame is held, the premix flame is held at the flame holder, and then it gets inclined of trying to burn into the reactant flow, so that the normal component of the flow velocity balances the flame speed. Of course it could be turbulent flame speed, so you get the shape of the flame, and therefore you get the length of the combustor, all those things, right. Essentially the idea basically there is, what is the residence time of the reactants within this region, okay. So there what happens is you are looking at LF over U. So if this is the length of the flame, then as the flow goes along the along this, it's going to be there for so long. While it is there, it's now diffusing this way, right? So the diffusion time scale is, as we saw yesterday, we have b squared over d, right? Therefore if you now say Lf over u is of the same order as b squared over d, then Lf, which is the same as eta max here, okay. So long as we were doing a heavy duty mathematics, we were using Greek like eta max and all those things, but this is just order of magnitude, just thinking about this. So we just started using Lf, right? That's the same thing. So Lf is ub squared divided by d, right? Now this is an order of magnitude idea, and it works reasonably well not just for Burke-Schumann problem or the Burke-Schumann geometry where you have coaxial ducts, but even for jet flames. So if you have a jet that's coming out of a fuel jet that's coming out of a pipe of certain radius r or diameter d, you could still say don't worry about the fact that you have to use the outer duct diameter. The order is not going to be significantly different if you use the inner duct diameter, alright. So in a jet diffusion flame you have only one duct, you don't have the outer duct. It's just entraining and diffusing with atmospheric quiescent air. Therefore you could simply say u small d squared divided by capital D, where small d is like the diameter of the jet, right, or the inner pipe. That's fine. Now what that means is two things you can look at. One, the diameter squared is proportional to the cross sectional area, right, and the cross sectional area times velocity is essentially the volume flow rate, like what you would measure with a flow meter, let's say, like liters per minute or meter cubes per minute or whatever it is, right. So this is basically volume flow rate divided by the diffusion coefficient. So you can look at it in two ways. One, either as a velocity burner diameter split or volume flow rate. If you look at it the first way, you learn two things. One, the flame height is going to be proportional to velocity and proportional to square of the duct diameter, alright. If you look at it the second way, all you get is the flame is going to be proportional to the volume flow rate, alright. So larger faster the flow that's coming, taller the flame is going to be, or larger the duct diameter, much taller the flame is going to be, or whatever is more the volume flow rate, larger the flame, longer the flame is going to be, right. That's what it means. Whatever we have done, we have been talking, whenever we talk about flow velocity, we had to bring in the Peclet number in our discussion and so on, but all the when we do that, and then I also said Peclet number is kind of like Reynolds number and so on, but we never talked about turbulence, right. We are not really worried about that. So where is the question of that why are we talking about it? The reason why we are talking about it is as we keep on increasing the velocity at some stage, or keep on increasing the volume flow rate or your duct diameter, right, at some stage you are now get into turbulent flows. And then what happens? Well, if you now have turbulent flows, the diffusion that's going to happen is going to be a turbulent diffusion, right, and there's not going to be molecular diffusion anymore. So we have to now factor in the turbulent diffusion. So the way you can do this is you can now look at the Schmidt number. SE is essentially equal to nu over d, or d goes as nu over SE, right. So now for a constant Schmidt number, let's not worry about how the Schmidt number goes. Typically we don't have to worry about that, and therefore LF goes as let's say ub squared divided by nu, right. So if nu changes, d changes through Schmidt number. Therefore if you want to talk about d as a turbulent mass diffusivity, you can think about it in terms of turbulent kinematic viscosity, and a turbulent kinematic viscosity is a flow dependent parameter, right. And the way it goes is, this goes as ub, so sorry u, right. The greater the velocity, more the turbulent viscosity, greater the diameter. This is because it depends on Reynolds number, right. So if you now think about this, then LF simply becomes proportional only to B. That means in fact I think I would feel a lot more comfortable, you can say also LF then is ud squared divided by d, where d is fuel duct diameter. I think it makes a lot of sense to talk about it in terms of, in the context of jet flames, and keep it as d rather than b, because I'm not thinking more about the outer duct diameter anymore, mainly talking about the fuel duct diameter. So what this tells us is the flame length is no longer going to be dependent on the flow velocity. It simply is going to scale only with the duct diameter, right. So if you look at the data, what you should find is, if you now plot your LF versus U, what you will find here is LF is proportional to ub squared by d, or ud squared by capital D. So this is linearly increasing with d, with u, right. So for small u you get a linear increase, all right, but then you get into a transition region where you transition to turbulent flows, and you now have a transition that now makes it insensitive ultimately to. Why is that? Because you have more and more mixing that's happening, and as more and more mixing is happening, you're having the fuel and oxidizer burn in stoichiometric proportions much closer to the burner, and that doesn't that becomes insensitive to the flow, because more and more flow, more and more burning can happen, and all these things are happening within a very short, within a pretty much constant distance, right. So that's essentially what's going on as far as turbulent mixing and burning is concerned, and therefore you have a pretty insensitive flame length to the flow velocity. So the interesting picture I have in my mind about these things is about our cartoons that we watch when we are kids. Like you have this dragon that spews fire, right, like the Spitfire dragon, then it is whoo, and then you now get a fire out of it, and you can clearly see from there that the greater the velocity, greater is the flame length, right. And of course and then the dragon really wants to hurt you and then keeps increasing the velocity, and the flame length doesn't increase anymore because it's become turbulent, and it starts blinking. What the hell, am I not able to make any impact? So it starts opening up its mouth more and more and then the flame length increases, and then it attacks the enemy, right. So we can learn quite a bit of diffusion flames watching cartoons. Thank you very much.